Kia ora. Here we're going to go through the answers to our interference worksheet for this week's learning. Okay, at the top we've got some language that we are going to want to be able to use. Nodal, antinodal, path difference, phase, constructive and destructive interference. Okay, we have here a double slit interference pattern, okay, where a wave has come through two separate holes. Okay, so we've got wave coming through one here and through one down the bottom here. We get a series of loud and quiet patterns projected out, and we can look at these patterns to understand the amplitudes of the waves at different points throughout. Okay, for this pattern here above, we're seeing that the wave has been scribbled out. It's been removed where there is destructive interference going on. Okay, so in these gaps here, this is destructive. Okay, and that's why it's been removed from the diagram. It's destructive interference. So the question for the worksheet is like this. Complete the following table of path differences for the other points on the diagram. Okay, they've completed point A for us, so we can have an example. So we want to look at the distance the blue wave has travelled from the slit and the distance the red wave has travelled from the slit to reach point A. Okay, so let's see. Blue wave, we're counting from the middle out to the blue wave. We've got one whole wavelength, two whole wavelengths. See if I can draw that. 1, 2. Okay, and for the red wave, I'm going to count from the other side. Okay, 1, 2, 3, and 4. Okay, that's where our 3 and our 4 come, our 2 and our 4 come from. And the path difference is simply the difference between those two numbers. Okay, this one over here is 4 minus 2 equals 2 wavelengths. Okay, let's do the same for B. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 7 lambda, 9 lambda equals 2 lambda difference again. Okay, let's do C. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 5 lambda, 6 lambda equals 1 wavelength. D. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. Oops. E. 1, 2, 3, 4. And 1, 2, 3, 4. We can see that this here should be in the middle. I'll draw it in yellow. 1, 2, 3, 4. That is an isosceles triangle with two even sides. Okay. No path difference. Cool. If, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, an isosceles triangle. 9 wavelengths, 9 wavelengths, 0 wavelengths difference. And G, our last one. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6. 8, 6, 2. Okay, so let's use this and do some pattern recognition to see what's going on. Okay, along the n equals 2 antinodal line, the path difference is, so on n equals 2 over here, we have B and we have A. Okay, and we look here, A and B both have path difference 2 lambda. Cool, that's what we're after. We're just using our pattern recognition there to, whoops, not the highlighter pen, 2 lambda. Cool. We could also see that it works on the other side. N equals 2 down here. On the opposite direction, we have G. Okay, so let's go look at G. And G also has, whoops, a path difference of 2 lambda. Cool. The n equals 1 line. What have we got? N equals 1. We've got C, we've got D. That's it. Okay, we'll do these ones in green. We've got C and we've got D on n equals 1. C and D. Nice. C and D on n equals 1. The path difference is 1 wavelength. And on the n equals 0 line, we have what? N equals 0, we have, goodness me, we have E and we have F. Okay, let's look at those. E and F. 0 lambda. Nice. That is all excellent. Okay, so it's using some path difference there. Constructive interference appears along these antinodal lines because the path difference is an integer number. Okay, integer number, that's really important. A whole number, 1, 2, 3, 4, 5. And we get destructive interference at nodal lines. Okay, nodal lines occur when the path difference is half of a wavelength. Okay, n plus or minus 1/2 lambda. Okay, that's where that's really important there. We're offset by half of a wavelength, meaning a peak aligns with a trough. Okay, so let's describe here, shall we, what we've got. For sound waves, the antinodal lines will be regions where the sound is what? And we know antinodal lines are the points of maximum displacement, so the amplitude is the biggest. So we know at antinodal lines, biggest amplitude for sound means they will be loud. Okay, for light waves, antinodal lines will be bright. And for water waves, the nodal lines will be where the water is high. Okay, a high peak in a wave. Nice. Okay, and let's look at 4 down here. We've got 2 speakers producing a note. That's great, and they're interfering, producing an interference pattern. Great, we're quite familiar with this by now. Now we want to look at each of these positions, A, B, and C, and try and justify why we're hearing what we're hearing from these speakers. Okay, so for A, we'll call this the left one, and this is our right speaker. At A, we're actually at a trough. At a trough. Oh my goodness. It's detecting my hand today. From L and A. From our right speaker, we can see that we're actually sitting at a peak. Therefore, destructive interference. Okay, peak and trough. We are out of phase, if we want to use a nice piece of physics language. Let's look at B here. From left, we are at a peak. At a peak from L and a trough from right. Therefore, constructive interference. Okay, we are in phase. This is a antinode. This one would be a node. Okay, we're trying to use our language, put all our language together. And C, we are at, oops, where's my little thing gone? Here we are at a trough from L and a trough from R. Therefore, constructive. Okay, interference. We are in phase. We are an antinode. Okay, I hope that helps with this worksheet.